So what I wanted to do today was show you another op-amp example, but just to make sure that all the pumps are primed, I wanted to go ahead and talk through the essential points of sort of our theory or our analysis technique that we will use for op-amps before I get into that. So first of all, just make sure we understand what an op-amp is. An op-amp is this collection of circuit elements that are generally put onto an integrated circuit, meaning it's kind of all built onto a chip of silicon, and then that is integrated into a device that might look something like this, kind of looks like a bug, right? 8 legs sticking down like this, perhaps. Anyway, but that complicated circuit is integrated into a package like this. And instead of us trying to understand at the circuit element level what all goes on inside of an op-amp, instead of doing that, we develop a couple of simple rules for how an op-amp is supposed to function, and then we just assume that the manufacturer of the op-amp did a good job of making a collection of circuit elements that really does behave according to that relatively simple model. Does that kind of make sense? So, the two basic rules that we need to understand are these. First of all, there are two inputs into an op-amp. There's a non-inverting input and an inverting input, and there will be no current that flows into or out of these legs right here. So if I kind of think about current flowing on either one of those two legs, there is a high enough, it's called impedance, essentially like a really high resistance internally inside of the op-amp, and it's not going to allow any current flow into or out of the op-amp on those two legs. So that's the first rule, is that we won't have any current flowing into or out of those two inputs. And then the second rule is actually one that depends on there being a feedback circuit built onto the op-amp itself. And that's a little bit beyond the scope of what we do in this class, like what are the rules for how you have to build that feedback circuit. In this course, you can assume that if you've been handed a problem, your instructor has already thought about what that feedback circuit should look like. So assuming it's got a good feedback circuit on it, then what you will end up seeing is that the voltage on the two input terminals will be exactly the same as each other. Okay, so that means whatever voltage, if I'm going to label some voltage, say Vx on this terminal down here is also going to be at that same voltage, right? And kind of assuming here some voltage relative, say, to a ground voltage or something like that. All right, so those are the two big rules that we're going to use to do op-amp circuits or analyze op-amp circuits. The last note that I would like to make before I get into doing this problem is that op-amp circuits actually have the capability of supplying energy into the circuit, okay? And because of that, a lot of times what you will see on the little op-amp circuit element is, sometimes in some contexts, you will see another couple of terminals sticking out of the op-amp, say something like that. And sometimes what they will be labeled as might be something like plus V or minus V, okay? I wanted to mention what that means if you see that sticking off of an op-amp symbol on a circuit diagram. What that refers to is that real op-amps actually need to have supply voltages coming into them so that they can supply energy, right? Now, a lot of times these two voltages are left off because assuming that the op-amp is operating in its sort of ideal zone, like within ranges of voltage values and current values and such, as long as the op-amp is operating in that ideal zone, it really doesn't matter what these voltages are. The big concept actually there is that you have to have enough positive supply voltage and enough negative supply voltage coming into the op-amp so that it's able to output, some voltage that it's actually probably generally not going to be able to go all the way to plus V or minus V levels of voltage. It'll get close maybe, but it won't go all the way. In some, if you go and look for op-amps, one of the terms you might start to see is, does this op-amp operate rail to rail? You might see that phrase whenever you look at op-amps. What do you think that might mean? kind of, yeah, so these two voltages, the plus and the minus V right here, those are sometimes referred to as rails, being sort of the outer limits of what kind of voltage might exist on your little circuit that you're building, right? So a lot of times those are sort of put onto big long terminals or something that might look like a rail, and so they would call this like a rail-to-rail level of voltage. And if you have a really good op amp, it's going to be capable of outputting voltages that are fairly close to the input voltages on the two rails. Okay? But I wanted to mention that, but it turns out that's not really going to be our focus, what those two terminals are, but it's probably good to know, like, if you see extra terminals on an op amp, what are those? All right? So what we're going to work on today is a problem where we don't necessarily need to worry about those two rail voltages. And here's the problem we're going to work. Okay? Here we have a circuit. Okay? It has a 9-volt source and a 0.4 amp current source. And it is fed into these set of resistors that are all hooked up to the op amp. You will notice that we didn't kind of label any kind of input voltages as far as the rail voltages onto the op amp there. And what we're supposed to do is find how much voltage we have at each of our nodes relative to the ground node. So you'll see the ground node down there at the bottom. We're supposed to find the voltages at every node in this circuit relative to that ground node. And let's secondarily figure out how much power this op amp is having to supply in this circuit. Okay, does that sound like a good set of things to try to do? All right, so where do you want to start with this? Okay, this is an op amp circuit, and so often what I think is a good thing to do is to start, actually a couple spots that sort of work together is where I like to start. One of them is it might be a good idea to label node voltages. Kind of start it almost like a nodal analysis problem. Okay, we have a ground node down here, and where should we label some voltages, you think? Say maybe at the input, right? So let's say that this is like a V, I'm going to put it down here. V1 would be like on this node right here. And let me go ahead and actually sketch in some, color in some stuff on these nodes so that we know what we're talking about with those nodes. So that's one node that I'm going to label that voltage V1. Where else might I have some node voltages? I have one up here, right? V2 maybe I'll call it, right? Where else? There's one up here. I'll call that V3. There's going to be another one up here on the top right corner. Call that V4. And then where the output terminal of the op amp connects in, that's going to be yet another voltage value right there. All right? And then maybe there's one down there below the 35. We'll get to that here in just a second. This is kind of the one that you're talking about right there. All right. So there we've labeled our voltages. I guess we missed one, right? We're going to label this over here as V5 as that output voltage. All right. But here's what we do next. Is there anything we can do on this op amp circuit to kind of use some of our rules that we developed right at the beginning? The two rules we have are no voltage across the input terminals and no current into or out of the input terminals. Did you have a comment? Okay, that's exactly right. So V1 that I have down here, because I've got that feeding into this input terminal of the op amp, and our rules say as long as we've got good feedback circuit hooked up to the op amp, we're going to have the same voltage on the two input terminals. And so I can label a node voltage right there at V1. So that's a good comment to make. What other op amp rules might we be able to bring to bear on this problem? The current that flows, and let me kind of show it over here. I'm running out of space, but let's say the current that flows into the op amp on that input terminal right there has what value? 0. So there's 0 current there. What about here? 0 there as well, right? So 0 current flowing into or out of the op amp on those two input terminals. What does that tell us about how much current flows through the 35 ohm resistor? There's 0 current flowing on the 35 ohm resistor, And if there's zero current on that resistor, how much voltage goes across that resistor? Zero. What does that mean as far as how does V3 relate to V1? They have to be equal to each other because no voltage is dropping on the 35 ohm resistor if there's zero current flowing through the 35 ohm resistor, right? So that's actually the first equation I'm going to write, is that V3 has to be equal to V1. And that's because no current. Okay? All right, so far, well, that's how far we've come. What do you want to try to do next, maybe? There is a path for current to go that flows all the way from the output of the op amp up through, it goes through where this voltage V4 is, through the 25 ohm resistor, through V3, through the 30 to V2. I have zero current, though, splitting off in that green shaded node up there. What does that tell me? That means I only have one path. It really means that functionally the 20, the 25, and the 30 are in series, right? They all carry the same amount of current. And so what I'm going to do here is actually define that current. I'm going to go ahead and label a variable that describes that current that goes up and around on that leg up there. And let me just I'll call it maybe I sub top. Basically meaning that's how much current flows up and around that top sort of path that goes up the top, over the top of the op amp. Okay? Why is that helpful, perhaps? Okay. There might be some interesting relationships that I can use here, one of which is going to be, we just said V1 is equal to V3, right? Did we say that? That means I can say V3 up here is equal to V1. How much voltage do I have from that location right there to this location right here? Tricky question. How much voltage, if I was to put my multimeter on those two big red dots? You'd have zero voltage. Why? They're at the same voltage, right? So what that tells me here is that I'd better be dropping 9 volts of voltage on this 30 ohm resistor. Why do I know that? Okay, yeah, there's a 9 volt change due to the source. That means I better balance that with a 9 volt change across my 30 ohm resistor. What direction does that voltage have to be oriented so that I end up with 0 from red dot to red dot? Right, so it would have to be oriented like this, I think you're saying, in order for that to actually end up being 0 volts. Okay? Well, what I have now is that I know a voltage across this 30 ohm resistor. Does that let me find current through the 30 ohm resistor? Okay. What is that current going through the 30 ohm resistor? I top. Right? I top, I already made a variable that goes up and through here. I can solve right now for how much current flows in that upper leg of the circuit just based on knowing what's going through this 30 ohm resistor. You see that? Okay, so let me go ahead and do that. I know here that I top is going to be equal to that 9 volts over 30 ohms. And if I punch that in, got 9 divided by 30, that ends up giving me 0.3 amps. Now that by itself was not necessarily a result that I cared much about, but it's going to be a very key element for the next step. What do you think that next step might be? Okay, so there is an actual nodal equation that might be handy for us to write at this point, and it is that number 1 node someone's mentioned, right? This node down here that I had labeled at V1 where I put a couple of red dots on there, right? Doing a nodal equation at that position is actually going to be very helpful. Go ahead and start doing it. We'll see why. Okay. I know that I have I top flowing into that node. I'm going to take exiting the node as being positive. So what should I count that 0.3 amps as? Let me put a label up here. KCL on node 1. Okay. What someone just said was that 0.3 amps that's flowing into that node is actually entering, so we're going to count it as minus 0.3 amps. What then? Okay. Then I'm going to have 0.4 amps leaving that node because of that current source. Then what? V1 over 40 ohms. Now, we have another wire that's attached to this node that feeds into the op amp. But a second ago, we just said what? Zero current on that leg, so we don't have to worry about the fact that it looks like there's a wire connected right there. There is, but there's no current flowing on that wire. Or you could put +0 on there, someone suggested, if you want to, you know, make an annoying looking formula. All right, so these would be all the current flows that I have coming into or out of that yellow node, and therefore it must sum to 0. And that tells me what? V1, I can solve this for V1, right? What it's going to end up being is, okay, if I add 0.3 to both sides and then subtract 0.4, that ends up giving me negative 0.1 amps multiplied by what? 40 ohms. And that tells me that V1 is just going to be equal to negative 4 volts. Okay, and so that's actually our first sort of important result that we get to, because it's asking us in the problem here to find the voltage at each node relative to the ground node. So we just found V1. Okay, you want some more good news? We just found V1 is equal to negative 4 volts. I can label V3 up here as what? Negative 4 volts again, right? Because we just said a few minutes ago that V3 is equal to V1. So I've really found V3 as well, right? V3 is also equal to negative 4 volts. Okay? And that's actually really handy because I can look at some of the relationships that happen in this circuit and just use Ohm's law to figure out some of the other voltages. For instance, let me scooch some of this down here. Okay. Can I figure out V4? How do I figure out V4? I could do a nodal equation for V4, or I could just say, I know how much current flows through this 25 ohm resistor, right? If I know that current, can I easily find the voltage across that 25 ohm resistor? All I do is take current times resistance to get voltage, right? That means that if I know the voltage on the green node, to find the voltage on the purple node, all I have to do is add the difference, right? So I could say is V4 is equal to V3 plus I top times what? 25 ohms. Right? I know how much current is flowing through the 25 ohm resistor. That tells me that I can figure out how much voltage goes across the 25 ohm resistor, which I would add that voltage to the voltage I have on the green node to figure out what the voltage is on the purple node. Okay? Are you following me? I'm seeing a few blank stares. Okay. So what this would be negative 4 volts, right, plus I top was 0.3 amps, and that is flowing through the 25 ohm resistor. Okay, and this should give me an answer for what V4 is. All right, negative 4 plus 0.3 times 25. That's 3.5 volts. All right, now because I did that one right there, what's your advice on how to find V5? Is there a reason to do anything different? Not really in terms of concept, right? We have a couple different values in there, but the concept really can be the same. V5 is going to be, help me write this, what do we have for V5? V4 plus I top, for that current flowing through that top path up there, times what? Times 20 ohms. Okay, so this is going to be 3.5 volts plus 0.3 amps times 20 ohms. Okay. So I already have that there, so I can just add to it 0.3 times 20. That gives me 9.5 volts. Okay, this was V4 and this was V5. Have we finished the first part of the problem? It said find the voltage at each node relative to the ground node shown. Okay, we haven't done V2. Good observation. Is there an easy way for me to get V2? Okay, to me it looks like V2 should be 9 volts less than V1. Why do I say that? Yeah, they got the positive side of this voltage source on the V1 side. That means you're going to have 9 volts less when you go to the V2 side. Okay, so let me scoot this down again. And we'll say V2 is just going to be equal to V1 minus 9 volts. And that is just going to be equal to minus 4 volts minus 9 volts. And what does that give me? Negative 13 volts. And that is V2. Okay? All right. We're done with the first part of the problem. What's the second part of the problem? Okay. What we want to do is figure out how much power is the op-amp itself supplying. Right? I suggest that our best strategy on this is to go back to Tellegen's theorem, which that's been a while since we talked about that. What does Tellegen's theorem say? Okay. I see some people saying, I don't remember what Tellegen's... Okay, Tellegen's theorem says that the sum of all of the power absorbed in a circuit has to be 0. Okay? It's essentially a energy conservation equation, right? It says however much power you are using, there better be something that's supplying that so that you end up with a 0 sum of how much power is being used instantaneously in a circuit. Okay? So what we can do is we can go to each of our resistors, and we know that the only thing a resistor can do is absorb energy. That's, you know, they have to absorb energy. That's the only thing they are able to do. And how do we figure out, for instance, how much energy gets absorbed in the 40 ohm resistor? I'm going to label that P40. How do I figure that out? Tell you what, I'm going to put some labels on here too, because that might help us keep track of what we're doing. Power absorbed by resistors. Okay. P40, how do I figure that out? You could use current. I think it might be easier just to use voltage, right? So we have V1, we figured that up earlier, right? Minus 4 volts squared over the resistance value of 40 ohms. So that's 4 squared divided by 40. That gives me 0.4 what? What is the unit on that? Watts. So that's a certain amount of power that's being absorbed there. Okay, what about the 15 ohm? Okay, probably do something very similar there, right? We can take our voltage V5 as that voltage at the output node. We had that at 9.5 volts. Okay, divided by what? 15 ohm resistance. Okay, so again, that's very similar, right? 9.5 squared divided by 15. So that would give me 6.017, we'll say, watts. Okay, that takes care of those two resistors. What about the 35 ohm resistor? How much current flows through the 35 ohm resistor? 0. I squared R says that's 0 power on the 35 ohm resistor, so I'll just leave it off. Okay? What about this chain of resistors up through the top? Yeah, we might as well just combine all those together because we have a uniform current flowing through those. It's like they're in series, right? So I'm going to just say P top. Okay? And because I already know the current flowing on that upper leg, let me take that current, 0.3 amps, and square it and multiply by what? The resistance, the equivalent resistance of that series of resistors, right? So that would be 30 ohms plus 25 ohms plus what? Plus 20 ohms. And when we punch all of those in, we will have 0.3 squared times 30 plus 25 plus 20. And that would give me 6.75 watts. Okay, so these are kind of some intermediate results because this is how much power we are absorbing, and I think that takes care of all of the resistors. What about my sources? So I'm going to say power absorbed. This is kind of an important point right here. Power absorbed by sources. Okay, when we evaluate these, we need to make sure that we are counting them as power absorbed. And then what I'm going to do, that those may have positive or negative signs. If it has a negative sign, what does that mean? It means it's actually supplying power, but I'm going to count them all as absorbing. That way I can just add them all up directly to figure out how much power the op amp is supplying. Okay, so let's start with, I don't care which one. Which one do you want to do first? Let's take the 9-volt source right here, and we understand that we've got I top flowing. What direction do we have power moving if I top is positive going into the 9-volt like this? It is actually supplying power in that orientation, so when we count it as being a power absorbed, we want to negate that. Okay, and the way I would probably write that, let me label this as P9 or something like that. I'm going to say the amount of power there is just voltage times current, so 9 volts. But I'm going to say that the current would have to be going the other way in order for it to be absorbing power. So I'm going to apply my negative right there. More than one way to kind of think about this, but I'm going to put my negative in front of my current that's flowing through that 9-volt source. And what that ends up giving me here is, that should be 2.7, right? Negative 2.7 watts. And remember, that's negative 2.7 watts of power that is being absorbed. That means what? It's supplying 2.7 watts of power. Okay? Now what about my other source? I'm going to call that P0.4. How do I figure that one out? What's the voltage across that source? V1. What is V1? Minus 4 volts. Okay? But ignore that you know the value of it for just a second and look at it how it's labeled. Right? V1, the presumption is V1 is a voltage with that polarity. Right? If we have a voltage with that polarity and a current flowing the direction of the 0.4 amps, is it absorbing power or supplying power? It is absorbing, right? Because you have a positive on the side that current is entering. That's the presumption, assuming V1 and I are both positive, it would be absorbing power, right? But the value of V1 is negative, so it's going to take care of the fact that it's not actually absorbing power, it's supplying power. Okay? So there, I'm going to, what do I need to multiply that by? That current value, right? 0.4 amps. So anyway, that's how I think of these two things. It turns out that the current source is also supplying power, and it's going to be at 1.6 watts. Okay? That is a negative 1.6 watts of power absorbed. All right. So I have handled all of my circuit components in this circuit except for the op amp. Now is when I can pull out Tellegen's theorem, right? What would that say? Sum of the power has to be equal to 0, or if there's only one element that I don't know, the power it must be supplying, I'm going to write it this way, power op amp supplied. What is that going to be? It better be equal to the sum of all the absorbed powers, right? So that's just going to be equal to 0.4 watts plus 6.017 watts plus 6.75 watts minus 2.7 watts minus 1.6 watts. Right? Whatever that kind of net amount of power that's being absorbed had better be supplied by the op amp. Okay? And so when we add all those up, I've got 0.4 plus 6.017 plus 6.75 minus 2.7 minus 1.6, and that ends up giving me 8.867 watts. And that's the answer to how much power the op amp is supplying in that circuit. Yeah?
So can we do this for every op amp that we're trying to find power for? We sum the power of everything else?
If it's possible for you to evaluate how much power is associated with every other element in the circuit except for the op amp, you can go back to Tellegen's theorem and use it to figure out how much power the op amp is putting in.
Okay, because I did it a different way and got the same answer.
Yes, there are other ways that you could possibly do it as well. Yep. One way to think about it is that you cannot have any power that is being delivered or absorbed on the two input terminals for the op amp itself, right? That can't happen. So if you know the current and voltage for the output, then you will know how much the op amp is supplying. So yeah, it is possible to do it other ways. The last point that I will make is that I mentioned we didn't show that we had the rail-to-rail, or kind of what those input rails would have to be for this op amp. Okay? Take a guess. What is the absolute minimum value that we have to have for the, kind of our plus voltage or minus voltage rails? Got any guesses? Okay. We have 9 volts. It's not on here anymore, but down here we have 9.5 volts actually. We have 9.5 volts coming out of the output terminal. There's no way that an op amp can do that, like put out a voltage that is not, or that is outside of what these rail voltages are. So absolute minimum value for plus V had better be 9.5 volts, or else it's not going to be able to supply that level out of the op amp output. Okay? So that's kind of more of a practical point, that if you are trying to implement an op amp circuit, it's important for you to have rail voltages that bound whatever your output might be of the op amp. Technically, you actually have to get a little bit beyond that level for real op amps. They usually have a hard time going all the way to the rail voltage. All right, cool. Any other questions? Fantastic.